The power of the Schwartz is with me. Hello. Spaceballs, I think, stars Rick Moranis, who just decided to stop acting. Didn't Rick Moranis get punched or something recently? Like he was just walking down the street in New York City and he got punched in the face. Now I have to look this up. Spaceballs, the movie. Yeah, Rick Moranis. Now I have to look up Rick Moranis news. Rick Moranis punch. Let's see. Yep. Rick Moranis was sucker punched in New York City. If you haven't seen Spaceballs, it's pretty good. It's a spoof on Star Wars. And the beginning of Spaceballs always cracks me up because you know how in science fiction movies they'll have the camera is looking at outer space, okay, and then maybe a ship will go by. It'll be like, okay, and then the ship passes by and you see the engines behind it. Well, at the beginning of Spaceballs, there's an image of deep space and a ship is going by, but it's like an incredibly long ship. So it's like literally like the first 2 minutes of the movie are just watching this incredibly long spaceship just go by, and it's really funny. Like it's one of those bits where the longer it goes, the funnier it gets. So the ship just, it's like a 10-mile long spaceship. It's funny. Maybe we'll watch that clip during the Zoom room. Okay. So let me get started here. I'm gonna zoom in one more, I think. So today we're gonna start talking about. So we're moving on from electric fields, and we're talking about electrical potential energy, which is, of course, measured in joules of a charge of size q. Okay. So we are going to call that U of x. All right. So specifically referring to electrical potential energy, because associated with each force is a potential energy. So there's a gravitational force, so therefore there's a gravitational potential energy. There's an elastic force, therefore there's an elastic potential energy. So there's an electrical force, so therefore there's an electrical potential energy. But based on that, we can define what is called the electric potential. Okay, so that is the subject of today. And electric potential is not the same thing as electrical potential energy. Okay, they're almost the same thing, but not quite. They're almost the same name, but not quite. So that's a little bit confusing, but I think that you guys are smart enough to figure it out. So if it says potential energy, that's the thing that's measured in joules. If it's talking about electric potential without the energy on the end, then that is another thing. Okay? So electric potential is typically denoted by V, and it is a function of position. Okay? And it is defined because remember, potential energy is defined at a given location. So you have a certain amount of potential energy at a certain location. So we take the electrical potential energy and we divide it by the amount of charge. Okay? So the potential energy that a charge has divided by the amount of charge, and that is the definition of electric potential. Okay? So we could get the units of electric potential quite easily. So the units of electric potential from this definition are going to be units of energy divided by units of charge. Energy is, of course, measured in joules, and charge is, of course, measured in coulombs. So electric potential is measured in joules per coulomb. Okay? But this has the special name. It is called the volt V. Okay? So I believe that's named after an Italian scientist. I want to say the name is Alessandro Volta. Okay, and he was basically the guy who first created a battery, which of course provides an electric potential. So that's why he gets the name. This is a little bit confusing because you could have an equation like if I said, what is the electric potential at location 1 meter? And then maybe that's 700 volts. So it can get a little confusing because you have a V on each side. Okay. But I think from context you can tell whether the V is talking about the unit volt or the function, the potential function. All right. So I think you're smart enough to tell the difference. But if I think it's just going to be really confusing, I will sometimes use, or you should be aware that sometimes the Greek letter phi is used for electric potential. Okay. So what I've noticed is that if the textbook is an American author, then they will tend to use V of X. And if it is a Russian, or let's just say not American author, they would tend to use phi of X. But I especially see this in textbooks by Russian authors. Okay? If you didn't know, I really like Soviet. The unit is a capital V, yes. I really like Soviet era physics stuff. It was an interesting time in physics. And I'm sort of fascinated by Soviet era physics. Okay, so what if we take this, okay, and we do minus the derivative of the potential with respect to position? Okay, by the way, I won't always say electric potential, I'll just say potential. Again, if it's not ambiguous, okay? So if it's ambiguous, then I will say electric potential. But if it's not, I'll just say potential. So what if I do minus the derivative of that? Well, charge is a constant, so you don't take the derivative of that part. And then you do minus the derivative of the potential energy. Now, if you recall, the derivative of the potential energy, negative the derivative of the potential energy, is the force. So I have that this is equal to force divided by charge. And in particular, because this is the derivative of the electrical potential energy, this is the electrical force. Okay? Now, if you recall, the definition of the electric field, the electrical force is equal to charge times the electric field. So if we take both sides and divide by Q, we actually get that this is the electric field. So minus the derivative of the potential with respect to position is the electric field. Okay? So let's just do a really simple example. What if the potential as a function of position is 7 over x squared? Okay. What is the force on a 2 coulomb charge? Let's say a minus 2 coulomb charge at x equals 1 meter. Well, first thing I would do is I would take the derivative. So minus dv dx, okay, is going to be minus, the exponent here is negative 2, so I have minus 2 times 7 over x to the 3. So that is going to be 14 over x to the 3rd power. And that's the electric field as a function of position. Notice how I'm not putting the vector arrow over electric field because I'm just talking about a one-dimensional problem. So plugging in 1, I get that the electric field at 1 is 14 newtons per coulomb, which means that the electrical force at 1 is going to be QE. So minus 2 times 14 is negative 28 newtons. So this would be a leftward force. Okay? It's a leftward force. So that's very simple. Okay? So can we go from the electric field back to the potential? So you can see that this is a rule for taking an electric potential function and going to the electric field. So you take the derivative of it. Okay? But can we go from the electric field and calculate the electric potential? And the answer is yes. So basically what we have to do is we have to do the reverse of this. So what if I did minus the integral from a to b of the electric field with respect to position? Well, electric field is minus the derivative of the potential. So I have a double negative here, which will get rid of that. So no more negatives. So I have dv dx dx. And then according to one of the fundamental theorems of calculus, first fundamental theorem of calculus, second fundamental theorem of calculus, I don't know. This is going to be equal to the potential at B minus the potential at A. So this is the equation that we're looking for. So minus the integral from A to B of the electric field is the potential difference between those 2 points. So this is another equation that we are going to need. Really briefly, I wanted to talk about how does this work in 3D. All right? How does this all work in 3D? So for example, because in reality, the electric potential is a function of 3 variables. It's a function of x, comma, y, comma, z. Okay? Your position horizontally into the page and out of the page and up and down. So what if your potential was like, I don't know, a constant times x times y squared times z to the 5th? Okay? If you want the x component of the electric field, that's going to be minus the derivative of the potential with respect to x. But we're going to treat y and z like they're constants. Okay? So we're just going to focus in on the part that depends on x, which is just x to the 1 power. Take the derivative of that. The derivative of x with respect to x is 1. So that term just disappears and these constants stay there. So I have minus c y squared z to the 5th. All right? If I wanted the y component of the electric field, I would do minus the derivative with respect to y, keeping x and z constant. So again, I'm going to focus only on the y part of it, which is y squared. Taking the derivative of y squared is 2y. So I would have minus 2 c x y z to the 5th. So see how I have 2y right there. Okay, and then the other terms remained the same. All right, and then the z component of the electric field is going to be minus dv dz, which, so for this, I'm going to treat x and y like constants and only take the derivative of the z to the 5th term, which is 5z to the 4th. So I have minus 5cxy squared z to the 4th. So if I wanted the full electric field as a function of x, comma, y, and z, that would be minus c y squared z to the 5th I hat minus 2c x y z to the 5th j hat minus 5c x y squared z to the 4th k hat. All right. So and so this process of taking the derivative of one variable while leaving other variables constant, this is called a partial derivative. Okay. And you'll learn about it if you take a class in multivariable calculus, but it's pretty easy. It's a really easy concept. And so a partial derivative actually has a special symbol. So this isn't the symbol for partial derivative. So you use a d, but when it's a partial derivative, you use like a especially curly d. All right. So this is the d that you use for partial derivative, to emphasize that it is not a total derivative, but a partial derivative. Like that. Okay. So actually, the electric field is going to be minus dv dx times I hat minus dv d. Actually, it's called del v del y j hat minus del v del z k hat. And this act of taking the derivative of each with respect to each of the three variables and multiplying it by the unit vector, that's called the gradient operation. So this can actually be written in shorthand as minus upside down equilateral triangle times v. So this is like a more advanced way, a more compact and cool. If you want to be especially cool in your physics, you can write it that way. That being said, this is not on the AP Physics C or the IB exam. So I just wanted to give you a little bit of extra information because I think it's interesting. Okay? Had like an eyebrow hair in my mouth or something. All right. So what is going to be the potential due to a single charge? Okay, so just like charge is the source of electric fields, charge is the source of electric potential. Okay, and the formula is the electric potential due to a single charge is equal to kq over r, where r is the distance from that charge. And q could be positive or negative, remember. So, yeah, important point, this is not r squared. All right? It's r. So this is a thing that people oftentimes are used to, that r squared, and then in the potential they forget that it's not r squared. It's just 1 over r. So why do I say that this is the electric potential due to a single charge? Well, let's take the derivative of it. What if we do minus the derivative of the potential from a single charge with respect to r? Taking the derivative of r to the negative 1 power is going to be negative r to the negative 2 power. And then that negative 2 power, if I have an extra minus sign, that negative cancels. So I get kq over r squared, which is, of course, the electric field due to a single charge. Right? So what I've just shown is that if the electric potential is given by this equation, then this relationship is satisfied. So that must be the right answer. Okay? So if you can find a potential where the derivative gives you the electric field, then you have the right potential. Yeah. Okay? So that's the right potential. So then what's going to happen is you'll have a bunch of charges. I don't know, so maybe you have 5 charges, 1, 2, 3, 4, 5. Okay, and I want to know, here's a point P, and I want to know what is V of P. What is the potential at point P? Well, what you're going to do is each of these charges is a certain distance away from the point P. Okay, and so to get the total potential at point P, it's going to be equal to the sum of the individual potentials due to the individual charges at point P. Okay, so I would be applying KQ over R 5 times. Okay, and I would add all those up to get the potential at point P. So I hope that makes sense. Just like electric fields. But there is one major difference. Okay, so there's an important point. Okay, there is an incredibly important point, which is this. The electric potential is a scalar. The electric field is a vector. So scalars, remember, have no direction. Vectors have direction. So this is really, really nice, okay? So remember, if we are combining 2 electric fields to get the total electric field, like let's say you have an electric field that's going this way and you have another electric field that's going this way, and we want to combine them to make the total electric field, well, what we have to do is we have to add them, but we have to worry about their directions. So we do that parallelogram rule, and we would find that the electric field points that way, okay? So here you have to worry about the direction if you want to know this electric field plus that electric field. Then the total is going to come from the parallelogram rule. Okay? But if it's a scalar, like the electric potential, we don't have to worry about directions because it has no direction. You would just do 5, I don't know, minus 3 equals 2. All right? So because of that, working with the potential is often easier. Then, once you're done with calculating the potential, you then generate the electric field from minus the gradient of the potential. Okay, so that is in like more advanced physics. That's usually how you would solve an electrostatics problem. So you wouldn't even go to electric fields because no one likes worrying about the directions of vectors. Okay, no one likes it. It's much easier to just add numbers and then take a derivative. It makes it kind of mindless. You know, I should make a joke about potential go burr. Potential go burr, produce electric field. All right, it's mechanical. So let's do a couple of examples. What if I have 2 charges, Q1, and Q1 is at the origin, and then I have another charge Q2 at, let's say, x comma y. All right? Or no, what am I trying to say? D comma 0. So it's horizontally across from that point. All right. And then we want to know what is the electric potential at a point P that is at coordinates x comma y. All right. So what we have to do is we have to figure out this distance. Now that distance is fairly easy. So the distance between x comma y and 0 comma 0 is square root of x squared plus y squared. All right. But then we also have to find this distance. And the main idea is here is this triangle. It's a right triangle. It goes up y, but it only goes over x minus d, right? Because there's less this horizontal distance is less than that horizontal distance by an amount d. Okay. So that means that this distance is not x squared plus y squared. It's x minus d squared plus y squared. All right. So then that means that the potential at point P is equal to k q1 over square root of x squared plus y squared plus k q2 over square root of x minus d squared plus y squared. Boom. All right. And that's for any point. So we could imagine the coordinates of the point are moving around. So we've kind of found the complete solution for two charges. All right. And then if we wanted the electric field, we'd take the derivative with respect to x or the derivative with respect to y. Let's do another example. What if we have a square of charges? Side length is a. All right. This is plus 2q. This is minus q. This is plus q. And this is plus q. All right. And we want to know the point P is in the middle of the square. So our R value is going to be half of a diagonal, which we've done that many times, where half a diagonal is going to be the side length divided by square root of 2. Okay, so we have a over square root of 2. And then we just add up 4 terms. So we're going to have k times 2q over r. Remember, it's not squared for the electric potential, plus k times minus q over r. All right, so that would be this term's potential at P. Then we have k times plus q over r. And then lastly, we have another one of those terms, k times plus q over r. All right, so these are equal and opposite, so they cancel out. These two, we have 2q plus q, so that's going to give 3. So I have k times 3q over a over root 2, which is just going to give 3 root 2 kq over a is our answer. All right. So there you have it. that is my lesson for today. So just to recap, we learned about the definition of electric potential. We learned about the relationship between potential and electric field. Okay. We learned about what is the potential due to a single charge, and how can we use that to get the potential at a given location due to lots of different charges, discrete charges. Okay. As you can imagine, in the next lesson, we will learn about continuum charge distributions, in which case it's going to be integration. Okay, so that is my lesson for today, and I will see you in the Zoom room.